Hello, and welcome to another lecture, this time on substitution to solve differential equations. So this is section 1.5 in the book, and you can get the book on this link that's in the description as well, and you can get the PDF as a web version, or you can buy a paperback. All right. So let's look at substitution, right? So it's basically just like when you're solving integrals. Substitution is a common technique. It's a bit of sort of ad hoc, just like for solving integrals. But you can solve certain equations that are not, in some typical form, where we have some sort of a technique, which basically, change the equation into something that we know how to solve. Right? So maybe best is to see it by example, what's happening. So, for example, this equation over here, well, it's neither separable nor linear, so we don't really know how to solve it at this point. But we notice that, it sort of has this underlying, it's y prime is something squared, right? So maybe we can make that something into a different function, right? So let's set the x minus y plus 1, right? Let's name it a different variable. Let's name it v, right? Now here, v is going to be a function of x, because, well, x is a function of x, and y is a function of x. So v, if it's x minus y plus 1, where y is a function of x, that whole thing is some function of x. And basically all we're going to do is we're going to rewrite the differential equation for y, the differential equation for v, in terms of x. So the independent variable is going to stay the same. We're going to change the dependent variable, and hopefully the new equation will become simpler, right? So we differentiate this thing because we need to somehow figure out how to substitute this. So we need to know how v prime and y prime are related, right? So we have to differentiate this. And again, remember that v and y are functions of x, right? So when I differentiate it, I get v prime. Then when I differentiate x, I get 1, right? And when I differentiate minus y, I get minus y prime. When I differentiate 1, well, 1's a constant, I get nothing. So v prime is 1 minus y prime. Okay, so that means that I can solve for y prime in particular. So I know what y prime is. I know what this thing is, so I can just plug in, right? So this equation over here becomes this, right? I substitute for y prime, 1 minus v prime, and for this x minus y plus 1 squared, well, this is just v squared, right? So I get 1 minus v prime is equal to v squared. Now, moving things around a little bit, I get, I can, solve for v prime, basically. So we get this, right? And we notice that this is actually separable. I can move, well, there's no x's really in there, and I can move all the v's on one side, right? So another way to write it is this way, as a separable equation that I can now integrate. So we do that, right? So we just integrate both sides here. We get this expression over here. Okay, well, we have to do something to simplify. So, we multiply by 2 to get rid of the 1/2. And then we take the exponential, right? And we get this, right? Now, over here, if you look at the plus 2c, right? That's basically just like multiplying by the whole right-hand side by e to the 2c, right? Which is really just c is an arbitrary constant. That's the constant of integration here. So really, it's just here we're multiplying the right-hand side by an arbitrary constant, well, a positive arbitrary constant because it's the exponential of something, but then we have these absolute values here, right? Well, so we can get rid of these absolute values by just making it an arbitrary constant, possibly negative. Basically, we write this, right? So this is something that we've done before as well, right? All right. So now one thing not to forget is, well, there are some singular solutions here, right? Something that I've skipped over here. Well, if it's maybe not so visible over here, but over here, if I separate the variables, well, v had better not be plus or minus 1, right? Because then 1 minus v squared would be 0, it would be divided by 0, right? So v equals 1 and v equals negative 1 are the singular solutions. So they're not the ones that I mean when I'm looking at this solution over here. All right, so now, well, we unsubstitute, right? We substitute, so we unsubstitute. We go back to, we were not interested in v, right? V was just a device to get our solution, right? So we want y. So we need to, basically unsubstitute, use these two equations to get back to y, right? Well, really, just use this equation. Sorry, not this one. You generally wouldn't use this one. So this equation to get back to y, right? All right. So first, let's start with v equals 1, right? One of the singular solutions. Well, you know what v is. V is this, right? So we have this. Well, that just means that y is equal to x. Let's look at the other singular solution. So the other singular solution is when v is minus 1, right? Well, again, I plug in what v is. V is this guy. And I get minus 1. So, okay, solving for y again, I get y is x plus 2, right? So we have these two solutions. So those are very sort of special solution, right? They don't have any constant in them, right? But they might be the one that you're looking for, right? I mean, generally, you start with an equation and an initial condition, right? So we don't have an initial condition. We want the general solution. That means we want also all the possible singular solution because we might be looking for them. We don't know, right? So we have these two. Let's get everything else. So everything else is coming from this equation. So well, we do the same thing, just substitute, well, unsubstitute, if I'm calling it that. Put the y back in, right? We know what v is. We stick it back in here. That's just, we get this equation over here, and we solve. Well, we put the x minus y on the right hand side, right? And now we could, well, we can expand this thing, and we can put all the guys with y on one side, so that we could factor out a y, right? And then we could divide by this guy, right, to solve for y, right? And so all the other solutions are going to be here, right? So basically, we have our, the general solution is this one, and this one, right? So if you have an initial condition, you plug that in. You first check if it's one of the singular solutions, right? If it's this or this, and if it's not, then you figure out which D would give you the, your initial condition. Right now, here. It's just a side note. You actually don't need this singular solution. It's fine to write it down. It's just you're writing down slightly more, but it's basically if you look at this, the d equals 0 actually gives you this solution, right? If I put in d equals 0, I'll have minus x minus 2 divided by minus 1. That's x plus 2, right? You can also see it over here, right? Because I have when d is 0, right? That's the same thing as the left-hand side being 0, and that's basically the same thing as the numerator being 0. Well, that's v equals -1. That was this particular solution. But that's fine. It's you cannot get this one by some d, right? There's no d that gives you y equals x. All right. Substitution is really the same idea as the way you do it over integrals. You guess. You try different things until something works. Right? It's more of an ad hoc kind of procedure, right? So sometimes there's certain patterns that you can look for, something that sort of tells you what to try to substitute. And usually you try to find sort of the most complicated part and try to substitute there. You know, and it's, you know, there's sort of these rules of thumb, but they don't always work, right? Especially, you know, if there's sort of more things that are complicated about the equation. And so here's some you know, short list of patterns to try, and it doesn't necessarily have to be exactly that, right? But basically, when you see something like y times y prime, well, you know, maybe trying y squared, right? Because when you differentiate y squared, you will get y times y prime. Same thing if you see y squared times y prime. Basically, whenever you see a derivative, you know, basically, you know, how you would do an implicit derivative. So a derivative in terms of y times y prime, right? You know, then you try the antiderivative of that, right? So when you see y squared, well, try y cubed. Okay, so it's not quite, you know, the derivative would be 3y squared, but you know, the constant gets lost in the substitution. So, okay, so similar things for cosine y prime, you try sine y. Sine y prime, you try cosine y. E to the y times y prime, you try e to the y, right? It's just basically the same idea. And, you know, don't, you know, just because you see this, don't say, well, you know, that's the only one that will work. I mean, these are things to try. And again, you try different things and see if one will work. You try to make the equation less complicated. Right, that's basically the idea. And there's nothing wrong with taking, you know, several different guesses, right? I mean, you try to you know, do the substitution, and either you can't make it work, it's hard to do, or you end up with something that's just not simpler, right? I mean, you might, you know, the substitution might work, right, but it doesn't make for a simpler equation. Right, that will happen, just like it happens for integrals, right? I mean, just because you can make a certain substitution, you get a different integral, doesn't mean that that integral is easier to solve, right? All right, so let's look at a couple of specific examples, sort of, you know, kind of general, you know, general classes of equations that can be solved by substitution. So it's not so much ad hoc, right? So, for example, Bernoulli equations, basically ones they sort of look like they're linear equation, but then there's this y to the n guy in there that's making it not linear, right? Well, as long as n is not 0. If n is 0, then this is just not there, right? Because y to the 0 is just 1. And then it's just a linear equation. The same thing when n is 1. Because when n is 1, it's q times y, and you could just put that on the left-hand side, right? And again, it would be linear. So we know how to solve those, right? So it's mostly about when n is not 0 or not 1. Right? Now, the interesting thing is that making this substitution, making v be y to the 1 minus n, will actually result in a linear equation. You have to be a little bit careful about, you know, divisions by 0 in this case, because you're dividing, but it's, you know, it gives you a linear equation that you then solve, and then you unsubstitute, and you get a solution, right? All right, so let's try it, right? So, let's suppose that we're given this equation over here. Now, it doesn't immediately look like a Bernoulli equation, but it sort of does, right? It has a y prime, a y, and a y to the fifth, right? Now, the trick is to, you can always, put this into this form, right? Just to check that really is a Bernoulli equation. Okay, it is, right? I can divide by x, and I can, right? If I divide by x, right, this disappears. This becomes x. X plus 1 over x, this x will disappear, and I can move that y to the fifth on the right-hand side, right? So my p is this guy, and my q would be the -1 in front of the y to the fifth. We don't really need to, figure out what p and q here are. We're just going to do the substitution. All right, so let's do the substitution. 1 minus n, in this case, n is 5. So 1 minus 5, so it's -4. So we're doing v equals y to the -4, right? And we differentiate, and just the power rule, right? I'm getting, -4 is y to the -5th power, right? Times y prime, that's v prime. And I can solve for y prime. All right, so we're gonna take our equation over here, and we're gonna substitute. We're gonna put in the y prime into here, right? So I get this equation over here. Notice I still haven't done the y's, right? It's just I've replaced the y prime. Well, the y prime was the v prime, right? Using this equation over here. Now we have to do this complete substitution. So we have to completely get rid of the y's. We have to get an equation in just the v's, right? So, all right. Well, that's easy. I have this thing over here. So, I mean, I could solve for y. But here, maybe it's easier because I already have notice I have the y to the fifth. I have a y, and I have y to the fifth. If I divide by y to the fifth, right, it's going to, disappear here, and then this y will become y to the -4th, and I know that that's v, right? So I do that, I get this equation over here, and now the y only appears as y to the -4th. That's v, right? So I get this equation, and that's linear, right? I can, write it in the more standard form, but that's a linear equation, right? Linear equation in v, right? So now I just need to solve this linear equation, right? Okay, so we have this linear equation, right? In the standard form, it would be written like this, where the P and F are these guys, and this is the initial condition. So y at 1 is 1, but we need an initial condition for v. So v at 1 is, well, it's y at 1 to the -4, because v is y to the -4, right? And y at 1 is 1, so 1 to the -4 is 1, so v at 1 is also 1. That's useful. And let's assume that x is positive, and that's okay because the initial condition is where x is 1, so we're really solving there in that range. And clearly, when x is 0, this is going to be a trouble. So let's just assume that x is positive. That's the range where we're solving. That's where our initial condition is. All right. So, well, we just have it's a linear equation. So we have a formula for it, right? We're using the integrating factor, right? This guy is the integrating factor over here. And, well, we just have a formula in terms of, definite integrals, right? So we're gonna just use that. So this is what it is, right? We could just write it like this. Okay, so where the p's and f's are the these guys, right? Let's simplify that a little bit, of course. So let's figure out what the integrating factor is. And well, we just need to figure out what this integral is, and that's easy. Just distribute the fraction, right? You have -4 -4 times 1 over s, right? So you know that's easy to integrate. Then you take the exponential, you get this, right? Now, if you look at this, this -4, if by laws of logarithms, right, that can go on the x, so it's really plus logarithm of x to the -4, right? And we're taking the exponential of everything. So by laws of exponents, that's the same as taking e to the -4x times e to the, and then this logarithm term times e to the 4, right? Or in other words, I mean, we could just take, that logarithm turns e to the logarithm of x to the -4. That just becomes x to the -4. So you could write it like this, right? Or maybe like this if you prefer. We also need to do it with a negative sign, right? So, well, that's easy because we just, taking the reciprocal of the exponential, that's easy, just negate the exponent. And for x to the -4, well, again, negate the exponent, so it becomes x to the 4th, right? So, so I just, take 1 over this, right? That's what this is, right? It's 1 over that guy, right? All right. And I just plug that in. So let's plug that in. So I have, this guy over here and this guy over here. I plug that inside here. Of course, well, inside it's in terms of t because, that the integral is, I'm doing the integral with respect to t. And there's no really closed form, way to solve this, right? Well, I mean, it depends on what again you mean by closed form, but no useful one that's really simpler than this. I mean, the computer doesn't really have any trouble with, with giving you, who's computing this for different values, right? So those are very nice, nice solution, right? So. All right, so that's our solution. Well, not quite for v, right? We need y, but in this case it's very easy. Y to the -4 is v, so y is v to the -4th, right? So the 4th root, 1 over the 4th root. So we do that, right? And we get this. Right, this is the expression that we get, and that's that's our solution. That's what we have, right? All right, all right. So let's do one more type that comes up from time to time, and that's if I have a homogeneous equation, just a fairly wide class of equations, but it's basically where it's y prime is equal to something that can be written as a function of y over x, right? And for that, we want to try this this substitution, right? Now, if you try that substitution, if you differentiate, you get this. Now, an easy way to get this is multiply by x, both sides, right? So you have xv is equal to y, and then differentiate, because you'll get y prime is equal to the derivative of xv, which, you use product rule, because, x is a function of x, v is a function of x. So, xv, if I differentiate the x, right, that it goes away, it becomes 1, right? So I get this v, and then plus x times the derivative of v, right? That's where that comes in. All right. So, well, so now you know what y prime is. And well, if whatever this function f, capital F is, well, I just plug in v into it, right? So this y prime is f of y over x becomes v plus x times v prime is equal to f of v. And well, we simplify a little bit. We write it like this, and we can also write it like this. The thing is separable, right? So, and it's separable. You always get a separable equation for any f. Now, of course, this capital F might be complicated and this might be hard to solve, right? If you remember, separable, well, we have a technique, but it involves integrating, right? And then solving for the v, right? So we always get in this implicit solution. So provided, well, however we want to write down this antiderivative over here, get this implicit solution, right, for v, right? And then we'd of course have to still unsubstitute, if we can, to get an equation in y, implicit or explicit, however we can do it, right? Now, notice that, you can already see it here. X equals 0 is going to be a problem, right? And, well, clearly a problem here as well, right? So, we generally assume that x is positive or x is negative. And that really depends on the initial condition that you have, right? All right, so let's look at this equation over here. And now it doesn't immediately look like a homogeneous equation, but you have to, work with it a little bit, and you write it out like this, right? Y prime is y over x squared plus y over x, right? So if I have my capital F, if I make it v squared plus v, right, that's going to put it into that form, right? Y prime is f of y over x. All right, and here, let's assume that x is positive, because that's our initial condition is at a positive x, right? Y at 1. When x is 1, y is 1, right? So there x is positive, so let's just assume x is positive. It's going to make things slightly easier. We don't have to put some absolute values in there. All right. So substituting, doing, v is y over x. Well, we get this equation over here. We get x v prime is going to be v squared. That's really the that's the f of v minus v, right? Which is the thing that comes up in the when we try to solve this. In terms of as a separable equation, we get this, right? This was the solution that we got before, right? You could just solve it immediately here. X times v prime equals v squared, and you solve it as a separable equation, right? If v prime over v squared is equal to 1 over x, right? And you integrate both sides, you get this. Right? Or you can just plug it into the formula that we just did. All right. And you do this integration, and you also notice that x is positive, right? So I don't have to put in the absolute values here. All right. Well, solving for v, we get this formula. Right? Now v was y over x, so you plug that in, we get this formula. Now we can solve for y just by multiplying by x, and we get this, right? So that's our, well, it's still not the specific particular solution that we're looking for, so we need to figure out what c is. So, well, y1 is supposed to be 1, right? So, well, we plug in 1 into here. And you notice that ln of 1 is just 0, right? So it's minus 1 over c is 1. Right? So therefore c is negative 1. So you plug in negative 1, so it's ln of x minus 1. Right? That's your solution. All right. All right. So that's it for substitution. It's a little bit of an ad hoc method, right? But it's sometimes useful if you have if the equation is sort of basically written in a sort of a more complicated way than it needs to be. You need to basically change variables to make it simpler, right? And of course, one could do one could spend a lot of time trying to solve different equation by substitution. But the main point is to know that this exists and it's possible to do. Sometimes that has to be done to put it into a form where we can actually solve something, right? All right, so that's it for this lecture. So see you next time.